Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting material is 1,2-dimethylcyclohex, 1-Na, 6-membered ring with a trisubstituted double bond bearing two methyl groups. The product is 1-methyl-2-carboxycyclopent, 1-Na, 5-membered ring with a double bond, 1 methyl group, and 1 carboxylic acid group. The ring has contracted from 6 to 5 carbons, and 1 methyl group has been oxidized to a carboxylic acid. Moving on to the next step. Ozonolysis of 1,2-dimethylcyclohex, 1-Na cleaves the double bond oxidatively. With reductive workup, Zn, the ring opens to give a decarbonyl compound, a linear dialdehyde or ketoaldehyde. Specifically, since both carbons of the double bond bear a methyl group, ozonolysis of the endocyclic double bond opens the ring to give a 1,6-dialdehyde with methyl groups on each terminal carbon, OHCCH, CH3, CH2, 2CH2CH, CH3, CHO. More precisely, the chain is CH3C is equal to O CH2 3C is equal to O CH3. Actually, for 1,2-dimethylcyclohex, 1-Na, ozonolysis of the double bond gives OHCC CH3 CH2 3C CH3 is equal to O, which is hexane 2,6-dione. Wait. 1,2-dimethylcyclohex, 1-Na has C1 is equal to C2 with methyl on C1 and methyl on C2. Ozonolysis cleaves C1 is equal to C2 to give OHC, CH3 fragment and. No, the ring opens, the product is a ditone dialdehyde, CH3-CO, CH2, 3, COCH3, I, hexane 2,7-dione. The ring has 6 carbons, cleaving C1, C2 bond gives a 6-carbon open chain, C1, CH3 is equal to O, C3H2C4H2C5H2C6H2C2, CH3 is equal to O, that is heptane 2,7-dione. Actually, the chain from the 6-membered ring, carbons C1, C2, C3, C4, C5, C6 in ring, cleavage of C1 is equal to C2 gives OHC, CH3, chain CHO, CH3. The open chain is CH3-CO, CH2, 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 COCH3 is equal to octane 2,7-dione. Let me recount. Cyclohexene ring C1 is equal to C2, C3, C4, C5, C6 back to C1. Cleavage gives O is equal to C, CH3, CH2, 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 C, CH3 is equal to O, which is octane 2,7-dione. 6 ring carbons plus 2 methyl carbons is equal to 8 total, but methyls are substituents. The open chain compound is CH3-CO, CH2, 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 CH2-CO, CH3 is equal to octane 2,7-dione. Moving on to the next step. Intramolecular aldol condensation, reagent 2, etona-etoH heat treatment of octane 2,7-dione with base, etona, and heat promotes an intramolecular Claisen or aldol condensation. The alpha carbon between the two carbonyls. Actually, an intramolecular aldol. The alpha carbon of one ketone attacks the carbonyl of the other ketone, forming a 5-membered ring. Since the alpha carbon of CH3-CO attacks the other C is equal to O, the chain counts C2, enolate alpha, C3, C4, C5, C6, C7 is equal to O. That's a 6-membered transition state giving a 5-membered ring after aldol and dehydration. The product is 2-acetyl 1-methylcyclopent 1-N1-ol or after dehydration 2-acetyl 1-methylcyclopent 2-N1-1. More precisely, the intramolecular aldol of octane 2,7-dione gives 2-acetyl 1-methylcyclopent 2-N1-ol after cyclization. which upon dehydration, heat gives 2-acetyl-1-methylcyclopentanone or an enone. The key product after intramolecular aldol condensation with elimination is 1-acetyl-2-methylcyclopent-2-N1-1 or specifically a cyclopentane with a methyl and acetyl group. Actually, the product relevant here is a cyclopentene bearing a methyl group and a COH3-acetyl-methyl ketone group on the double bond, i.e. 2-methyl-1-acetylcyclopent-1-Na. And for the final step, NaOCl, sodium hypochlorite, bleach, reacts with methyl ketones via the haloform reaction to convert COH3 into COH2Na, sodium carboxylate, plus CHCl3. This converts the acetyl group into a carboxylate. Protonation of the carboxylate gives the free carboxylic acid, COH2H, yielding the final product 1-methyl-2-carboxycyclopent-1-Na. Sequence 1. Ozonolysis to open ring and form diketone. 2. Intramolecular aldol condensation to form cyclopentane with methyl ketone. 3. Haloform reaction to convert methyl ketone to carboxylate. 4. Acidification to give carboxylic acid. This matches option D 1, 2, 3, 4. Why other options fail? A. 1, 3, 2, 4. Using NaOCl before aldol condensation would react with the open-chain diketones methyl ketones before ring closure, destroying the substrate needed for aldol. B. 1, 2, 4, 3. Acidifying before haloform reaction does not convert the ketone to acid. H plus alone cannot oxidize a methyl ketone. C. 1, 3, 4, 2. Same problem as A. Haloform before aldol loses the methyl ketone needed for ring-forming aldol. Therefore, the correct answer is D. Therefore, the correct answer is option D.